Hey, it's me, Miss Wesley, and I'm back to join you for the next segment in the continuing saga of limits, the basis of calculus. So we're on limits packet page 12, and we're going to start talking about these non-algebraic functions. Sure, it was kind of cool, it was kind of neat when we could do stuff on the previous pages with using a conjugate to rationalize a numerator or denominator and find a limit. We could factor and cancel when that was applicable, and we could even simplify rational expressions. But what about stuff like you see here, 9, 10, 11, and 12? Maybe we'll get into some trig identities that can help, but I don't think there's factoring or conjugates that could help us with these initially. So have the calculator ready. We'll get to those. Quick little joke. Why the teacher have her eyes crossed? Because she couldn't control her pupils. Let's look at number 9. It says this is actually a famous limit that we're about to calculate. The limit that as x approaches 0 of 1 plus x to the 1 over x. You get the weirdest indeterminate form if you try to direct sub in. You get 1 plus 0, so 1 raised to the 1 over 0. That just scares me to even write. So because this isn't very helpful and because there's really no factoring or conjugate I can use, we're going to try a method just using the calculator. If you were to graph this function, you actually would get some like seemingly continuous line. But we know there's a hole in the graph. We know that you're not allowed to plug in a 0 because you would get division by 0 in that power. So we can't plug in 0 precisely into this. Well, we could plug in values that are really close to it and average a couple outputs. That's going to be our strategy. Pick two values that are symmetrically really close to 0, one right above it and one right below it. We'll plug those in for x. So here's what I mean. I'm going to just arbitrarily choose the value 1/1000th below 0, negative 0.001. I'm going to find the output value when x is equal to 0.001. I'm going to average these two values together. If those are legal values to plug in, I'll probably be able to estimate just exactly where that hole would be. And I'll use the calculator the whole way. I'm going to go to the calculator. We're not typing in any trig yet, but you might want to make sure you're in radian mode now. And I'll go to y equals and type in the original function expression, 1 plus x to the power 1 over x. And maybe I'll look at the graph for starters on a standard zoom 6, negative 10 to 10, so I can see that function. Now my calculator actually does show that little skip in the graph there, and just hitting trace now is basically what we're trying to do here. We're just trying to get into the ballpark of where that limit would be and make a good estimation. Right now it says when x is 0, y is blank space because y is nothing. You go right above it, right? Not as close as I want it to be, but you're at a 2.957. You go right below it, or right, like at the x value above 0, you're at a 2.5. Maybe the limit's around like a 2.8, 2.7. Let's get some more accuracy here. This second and calc menu can enable you to type in any value and get the any x value, get the y back. So let's type in our first one, negative 0.001, and see our output is going to be 2.71964. So we get approximately 2.7196 to 4 decimal places. If I do the same thing, I want to add second and calc for a value. The value when x is equal to positive 0.001. And you get 2.7169 this time. So this should be a plus, and then 2.7169. And I want to average those. So use the calculator, average those two values. You get around 2.7, something that rounds up to 2. For me, for now, this whole thing's just an estimation. That's an okay answer. But I said this was a famous limit. Does this number remind you of some famous irrational transcendental value? And it is the natural growth constant e. This is an alternate definition for the constant e. The definition as, and it kind of comes from the same formula we use to get interest on money investments. It's a 100% plus your rate of interest there, so plus x, raised to the 1 over x. For this function, as x gets closer and closer to 0, your limit's going to be exactly e. So for us, a 2.72 is going to be fine. All right, let's look at 10. Is there going to be an answer? Actually, in this one, we can tell that there will be. If we do a direct sub, we get e to the 0 minus 1. So that's 1 minus 1 up top, a 0 up top, and we do get a 0 on the bottom, meaning there's just a hole here. There should be a limit. Let's find it. I'm going to do the same thing. It's kind of funny because coincidentally, these 4 examples are all around 0. So I'm just going to decide to go from 1/1000th below 0 on the x-axis, see what the output is, to 1/1000th above 0 on the x-axis, and average these two outputs. So let's try that in the calculator. I'll just get a new graph in here, clear out my old one, and do e to the x minus 1 is your numerator. So e to the x minus 1 divided by x. Maybe I'll graph it on a Zoom 6 for starters. And I see it should skip a dot there, but let's find it. I'll just jump straight to second in calc value. So for negative 0.001, let's say, see what this is really close to. So a 0.9995. And then let's see what's happening at positive 0.001. 1.0005. Does this remind you of a certain whole number we could probably guesstimate? I could say 0.9995 was our first output. The second one was just so close to 1, just right above it. If I average these, I get exactly 1. So here we're looking at a graph that would have had a closed-in dot at 0, 1, but it is a hole, and it does get to be a limit. Okay, so don't be afraid to use the calculator to estimate for those. For 11 and 12, same idea, but 11, actually, can you circle these two? 11's actually going to help us with 12, and we'll see why in a second. Same deal. If I do a direct plug-in, sine of 0 is 0, and 0 itself is also 0. There should be an answer to this. Same exact setup. Let's make this roughly equal to two numbers that are symmetrically really close to right around 0. So f of negative 0.001, f of positive 0.001 over 2. Maybe pause the video and try this one. Type it in radian mode in your calculator and see if you get two values. I'm getting numbers that are right around 1 again for this one. I'm getting 0.69s and then an 8 for both of those, 0.9999998. And why is this happening divided by 2? I'm guessing I'm so close to 1 again. I want to put 1 with a question mark here. And maybe I should take that time to see what this looks like in a calculator on radian mode. So I'll go sine of x divided by x. And I want to see if this graph is looking like both sides are approaching 1. Like if biological guess. Well, yeah, it jumps up. If I were to hit trace here, at 0, it doesn't give me an output, but right to the left and right of it, the table values, the function values look like they're approaching 1. And what's cool is we might be able to put the calculator away now to try the very next two non-algebraic examples, because I wonder, let me start this one. I wonder if we decide 1 is the limit for number 11. Could you get this expression out of this expression? Do you see any similarities? Well, I see they both are being divided by x, and I see if I draw on some of my easy trig identities, like the quotient identities here, I could probably work my way into finding this and that. Tangent, right? AKA sine over cosine. So this is the limit as x approaches 0. Let's see if some trig identities gets me through this. Of sine of x divided by cosine of x. And that whole thing needs to be divided by this x on the bottom. I'm going to make this so it's not a complex fraction, and I'm going to say dividing by x is the same thing as multiplying by 1 over x. And what do you know? A little bit of a rearrangement gives me exactly the expression I had in number 11. I could just move things around and call this the limit as x approaches 0 of the sine of x over x, which we kind of just worked with, times 1 over the cosine of x, which might be able to be directly substituted into. Let's see. Well, we just got finished finding this limit, and now we just have to be concerned with that one. We found in the last problem. Let me recopy the limit notation. So limit as x approaches 0. We just estimated with a calculator that the answer to this limit was the number 1. So I'm entitled to use that now, use what I already know. So that part of the limit is just the number 1. Is this part of the limit okay for a 0 to be directly substituted in for x? And I think the answer is yes. This is going to equal 1 times 1 over the cosine of 0, and luckily that quadrantal angle, 1 over, what is the cosine of 0, is just 1. So this limit also happens to be 1, and the work that we did in number 11 non-algebraically really helps with 12. Same thing's going to happen with 13. I get so excited when the trig is involved, and we'll see if maybe just some, maybe not the exact same thing, but maybe some identities can get us through this so that we don't actually have to approximate on the calculator. It says secant over tangent. Well, let's get, I think back when we were proving, right, trig identities, doing some verifying problems, one of our basic techniques was kind of like we did in the last question. Get the whole expression in terms of sines and cosines. So that's a good step 1. Let's do limit as x approaches 0. What do we know? Secant, we can write what? 1 over cosine of x. Divided by tangent of x, and we know tangent is sine over cosine. So dividing by tangent, sine over cosine, is just like multiplying by its reciprocal. So I'll bring this to the top. Ooh, this is good. Cosine of x over sine of x. This is great because you've got that common factor. So it's like we can use the dividing out technique. And now let's reassess. Now in the simplified version, we're supposed to find the limit as x approaches 0 of, I guess all we have left is 1 over the sine of x. Should I reach to a calculator? Do I need a calculator? Well, actually, we're in a whole different case here. We've been doing a series of a lot of problems with and without the calculator where a plug-in gives you exactly 0 over 0, and that's not the case here. If I tried direct substitution into this expression, I would get a 1, because 1 always stays a 1, that's a constant, divided by the sine of 0, which is 0. I agree with you there. We got to think back. This is the perfect time to review. Anytime a plug-in gives you a non-zero value, so non-zero number divided by 0, what was the easy solution? There is a VA happening here. So because we're getting 1 over 0, which is a non-zero over 0, I'm going to put the easy answer of dne, and I can predict that there won't be a limit here. You might be able to give a one-sided positive or negative infinity, but there's going to be a vertical asymptote in this graph. When you have the time for it, it's obviously never a bad idea to check this answer with what it looks like it should be on a graph. I typed in secant over tangent to Desmos. Really, I should have just typed in cosecant because that's essentially what you're graphing. You get this cosecant set of almost parabola-like branches that would sprout off of an original parent graph of sine. And notice, at the x value in question, at x equals 0, there is no limit. Left-sided limit, all you could say is negative infinity. Right-sided limit, maybe you could say positive infinity, but there is no limit as a whole. There's a VA. And that was some good practice with non-algebraic techniques. I wanted to end the lesson on the next page, on the very next page, page 14, right in the middle of the page where it says find the limit of the difference quotient. Difference quotients are going to become more important actually in the second major area of calculus when you guys get to derivatives. But as a spoiler, this expression actually in some weird way comes from the slope formula, the slope between 2 points on a line. We have the algebra skills to be able to easily calculate this limit though. And we can be confident in the fact that there will be a limit because I know if I plug in 0 for h here on top and bottom, I'm going to get that indeterminate form 0 over 0. So let's give it a try. Limit as h approaches 0. We should be able to evaluate both parts of this. F of 3 plus h, that means go to this function. Everywhere you see x, plug in a 3 plus h. So it's 3 plus h squared minus 1. That is f of 3 plus h. What's f of 3? That's a question you've been asked since you first learned about functions. Evaluate this expression at 3. So minus, what's it going to be? 3 squared minus 1 gives you 9 minus 1 as an 8. On the bottom, just a lonely h. And while we can't directly substitute yet, I bet you in 1 or 2 more steps we're going to be able to. So limit as h approaches 0. There's some simplifying we can do, right? 3 plus h squared, can you square that binomial? So make it 9 plus 6h plus h squared. Minus 1 minus 8, so this is kind of lucky. Minus 1 minus 8 gives you a minus 9 to further be able to simplify the top. The plus 9 and the minus 9 completely going away. Can you do a direct sub yet? Ugh, not quite. You still get 0 over 0. So let's do one more step, right? A factoring and dividing out. Limit as h approaches 0. Let's pull an h out of the top and get 6 plus h. And then we've got that lonely h sitting on the bottom that gets to cancel now. Finally, we can do a direct sub after a few little steps of simplifying. 6 plus 0 is your limit. The limit is 6. And if someone asks you what's the derivative value, what's the rate of change in this function or the slope of the tangent line at x equals 0, that you just figured it out. The slope of the tangent line is actually going to be 6. Now, I've gotten a little bit ahead of myself, but it's nice to know we can use those algebraic techniques still. All right, enjoy the rest of your day.